Okay, everybody, so time for part 3 of trig substitution, where I just hope to do a few more problems that are along the same style as the others, but involve some other things that I haven't been able to show you yet, okay? So I have a problem here, and then I have my guidelines handy also. So this one appears to have a difference of squares. And remember, when it comes down to choosing your substitution, I divided it into two cases, and I said the problem will have a difference or a sum of squares like this. Okay, so it appears to have a difference of squares, but not quite. So let's look at these together as best we can. Here I say that the integral contains a squared minus x squared. A is a constant. Okay. It doesn't say a squared minus like some other number times x squared. You know, notice I didn't leave room for a 4 right there. You know, 36 minus 4x squared just does not fit this. Okay? And we use this the way it is. We can't ignore the fact that that 4 is there. So this one, you know, is doable by that case, but it's going to take a little bit of work to start with. Okay, all right, so here's what I'll do. To start with, I'll say, well, for that part, I'll factor out the 4, since this does not allow for the coefficient of the x squared. Okay, so I'll factor out the 4. So here's what I'm looking at under the root. I'm looking at 4 times 9 minus x squared. Isn't that right? Yes, 4 times 9, that's 36, and then 4 times x squared, that's 4x squared. So under the root here, I'm looking at a 4 and a 9 minus x squared. And square roots apply across multiplication, so you could see this as root 4 times root 9 minus x squared. So, okay, when I bring this 4 out of that root, it's going to be a 2. That's all I'm really trying to say. So let's say that we'll have a 2, and we'll be left with root 9 minus x squared dx. Okay, so that's more like it, right? So let's say that, okay, well, we'll really work in this problem. It's equivalent to that one, same thing, but this is in an acceptable form for the guidelines, all right? And it's all about using the guidelines. So, okay, so say we get to that point, and then I try to figure out how to use those guidelines. So the wording was that the integral contains a difference of squares. It contains a squared minus x squared, right? That was my statement here in my guidelines. And the form is 9 minus x squared. And so that would make a be 3. Okay. So then what's the substitution then? In that case, our integral contains a squared minus x squared. We will substitute x as a sine theta. All right, so we're going to sub x is 3 sine theta. All right, so that's what's going in for the x. The dx, the differential, that's a different thing. And so for the dx, that will be 3 cosine theta d theta. And then that should do it, right? I followed the guideline. You know, I made the integral fit it. This is what it said to do, and so I can expect that to work. All right. So if I do that in this step, then I'll get the 2, right? I'll have the root, okay? So let's see. I'm going to have 9 minus, okay, so suppose you put this in there for x and you square it. You've got 3 squared and sine squared. So let's say 9 sine squared theta, okay? And then the dx, okay, so the dx, that's going to be 3 cosine theta d theta. And that would take care of it. Substitution is made. Now, once you work these, then predictable things start to happen. Okay? Might not seem so at first, but there are certain things that happen in just about every problem. When you substitute sine, in this case of the difference of squares, when you decide to substitute sine somehow, then you'll use the identity 1 minus sine squared at some point. You can expect that. Here I've got 9 minus 9 sine squared. So let's do a little bit of breakdown on that. So under the root right here, if I factor out 9, I'm going to have 1 minus sine squared. I'm going to have 9 times 1 minus sine squared. And then I can use an identity to reduce further. 1 minus sine squared is cosine squared. So I have, under this root, 9 times cosine squared theta. Okay? All right, that is what's sitting under that root right there. Now, you can expect that. This substitution will lead you to expect to use that identity, that 1 minus sine squared is cosine squared. Lots of other things may happen in addition to that, but this part I can expect. Okay? So let's do this. To take this all apart, I'm going to have 2, and then root 9 times cosine squared. What's root 9? That's going to be 3. What's root cosine squared? Cosine, all right. And then I got 3 cosine over there. All right, like so. That's what I get. Now let's collect some things together. 3, 3, 2. Those are all constants, all multiplied. So I really have, if I would like to pull that out of the integral, I have 18. Okay? And then in here, cosine times cosine. So I have cosine squared theta d theta. All right, so now we're to that point right there. Now, the goal then is to take this original problem, decide and make the substitution, and then get it to a point where you know how to work it, right? That's always the goal. What do we do with cosine squared, though? Have we seen that before? We've seen that before. It was in the lesson on trigonometric integrals, not to be confused with trig substitution. So there was a lesson that I did and some videos I did about how to deal with even versus odd powers of sine and cosine. Okay? So yes, there's an identity that we talked about and that you should use in an integral with cosine to an even power. All right? Given that we really have no options for working this one besides using identity. This is not a u substitution problem right here. Okay? So it was that you take cosine of an angle A is 1 plus cosine of double the angle A all over 2. That's the identity that's in effect right here. All right. So okay, let's do that. That is from a previous lesson. Previous videos have been made about that. The problem we did was probably what's the antiderivative of cosine squared of x or something like that. Okay, so you can look back at that if you need to. So let's see. All right, I'm going to put, based on what I have here, 1 plus cosine 2 theta over 2 d theta. All right, so let's do a few things here. I'll go ahead and remove the 2. What is the 2? That's a 1/2, isn't it? So I'll get an 18 times a 1/2. I'll get a 9. Okay? And that'll leave me with 1 plus cosine 2 theta d theta. Okay. All right. Now, this is the point where it's workable. 1, a constant, is not hard to integrate. Cosine 2 theta, well, the way we do that is use substitution and let u be 2 theta. It will be cosine u du. That part of it will be. All right? So here's what we'll get then. 9. What's the antiderivative of 1? D theta. 1 with respect to theta. That'll be theta. And then this will be sine 2 theta over 2. Okay. There we go. Now, all right, I did the integration. I found the antiderivative. Okay, so I got that part. Now, let's do one more thing before we figure out how to get this back in terms of the original variable, okay? So I'll multiply through by the 9. Let's say I got 9, so theta. Here I'll get 9 over 2 sine 2 theta. Okay? Now the way that we get theta back in terms of x is different than the way we get sine 2 theta back in terms of x. Okay? So two different things happen here. One, if this is my original link between x and theta, then I can solve this directly for theta and just plug it in right there. Okay? So in other words, like I could say, you see this. All right? You see that. I can say sine theta is x over 3. Okay. And I can say that theta is inverse sine x over 3. Right? That's all allowed. This tells you what theta is to be directly in terms of x. That goes here. Okay? That goes right there. But what about this part, sine 2 theta? We'll need to draw a triangle for that part. All right, so let's see. Here, this tells me some information about my angle. So let's see. If sine of theta is x over 3, what's that mean about theta? Well, you know, I've showed you problems already where I've drawn a triangle to illustrate that. And you can say, well, if sine of theta is x over 3, it might look something like this. And sine is opposite over hypotenuse. So that means that this is x and this is 3. Okay. And then we could solve for this part down here. This will be root 9 minus x squared. Because the Pythagorean theorem, this side squared plus that side squared has to be this side squared. Okay? So you know two sides of a right triangle, you can find the third side. Now, you use the triangle to do this part. But there's a catch. Okay? Sorry to tell you, there's another hitch in this problem. If that's theta, what's the sine of the angle twice as big? Like, if that's just a generic picture, how would I even, like, I don't even know how I'd draw, like, what that angle looked like if it was twice as big. It's just a generic angle. It's just a symbol, really. So I need to get this in terms of that picture right there. That's theta. That's 2 theta. Okay? Now, maybe at this point, it won't surprise you if I tell you there's an identity for it. All right? So yes, there's an identity. When, you know, if you like to have some notes handy, you might want to have a list of identities. I'll show you the ones that are commonly used when we do the problems, but that's the double angle identity for sine. Okay? So sine of double angle A, so sine of 2A is 2 times sine A cosine A. That's what we want. That will put what I have here, 2 theta, in terms of theta, which I have in my picture. All right? So let's put that in. Let's say 9 theta plus, and then I want 9 over 2 times 2 sine theta cosine theta. So that's just going to be a 9 sine theta cosine theta. Okay, plus c. Now I've got everything I need. What is theta? Theta is inverse sine of x over 3. So I'll get 9 times inverse sine x over 3. Okay? Now, carry down the 9. What's sine of theta? Well, see it? See that triangle right there? Sine is opposite over hypotenuse, so it's x over 3. Okay? what is cosine of theta? See, theta's right there. Cosine is adjacent over hypotenuse. So that will be root 9 minus x squared over 3. Let's see. So I think we got it then. Our answer, 9 sine inverse x over 3. Can't do anything to reduce that. Here on bottom, I got 3 and 3. That's 9. I got 9 on top. Those cancel. Plus x root 9 minus x squared plus c. Okay. Finally, I got, like, just at the last minute. I was about to run out of room. Hate to have to get a new sheet of paper out to continue one single problem, but that's that's just the way it is. I told you when I made my very first video, part 1, that these trig substitution problems can take a lot of steps. I had to use several different identities. I put them in red ink. I wanted them to stand out. You plan to use them in the future. Not in every single problem, but they do come up. I can say, though, that with the sine substitutions, you can expect to use the identity 1 minus sine squared. It's cosine squared, though. Okay? So let me see. Real quick, as far as some algebra stuff, I said I would do a little reviewing here and there. About this root, simplification, when I said root 9 cosine squared is 3 cosine. Somebody could say, why didn't you do that right here? Well, roots distribute across multiplication, and so do exponents. Exponents and square roots distribute across multiplication and division. They don't distribute over addition and subtraction. All right, so I cannot reduce this root right here. I don't have that option. It can't be done. I'm stuck with it. I have to work with it the way it is. But I guess the way that the trig substitutions work and the reason they're effective is once substituted, they turn what was subtraction into multiplication. And that's the real power behind simplifying the roots that we get in these problems. Okay. So, all right, we finally got that one. All right, let's see. There was one more that I wanted to show you. Okay, here it is. This one here. All right. So there, 1 over x times root 4 plus x squared. Okay. So I've showed you the cases, right? And I've probably talked about those enough. Use them in much the same way every time. All right. Now, let's do this. I'll just tell you that the substitution is going to be x is equal to 2 tangent theta. All right, now you can use my guide that I gave you, but what's going to happen is I'm going to put this in, and I'm going to get the identity 1 plus tangent squared, and I'm going to say that's secant squared. That's how the ones where you substitute tangent are going to work out. I need a 2, though, because 2 squared is 4, and I'll factor the 4 out to get 1 plus tangent squared. You could think about it like that if you want to. If you prefer to do it by the letter and actually consult this, then go for it. You can do it that way. But this is what's going to work. So there's x. Here's dx. 2 secant squared theta d theta. All right. So let's put that in and see what we get. Okay, so I'm going to get this on the bottom there. X is 2 tangent theta. Okay. Then I get root 4 plus x squared. So that's going to be 4 plus, and the x is 2 tangent theta. What happens if you square 2 tangent theta? You get 4 tangent square theta. And this is the part where I was saying I could see a little bit ahead. I knew I was going to get 1 plus tangent squared. That's the identity that shows up at some point with this substitution. Because the 4, I factor the 4 out, I get 1 plus tangent squared. I'll eventually do that. That's where I see that it's going. Maybe you see it too. If not, that's just what it looks like when you put it in. Okay. Now, for the dx, 2 secant squared theta d theta, I've said before in other problems, it's not like those are all stuck together. We can put the 2 and the secant squared theta over here and leave the differential out there if you want to. All right, so we got some stuff to simplify for sure. Let's start with this. Now, I'd like to just work on this part without having to rewrite the whole thing just to work on the part inside the root. So the part inside the root, suppose I factored out a 4. And I aim to do that because if I factor out a 4, I'm left with 1 plus tangent squared. And that simplifies by way of identity. 1 plus tangent squared by identity is secant squared. And that gives us a way to simplify this root right there. Okay? So that is what's sitting inside the root. So, all right, let's do this then. I get 2 secant squared on top. And I know I could have canceled the 2's, but all right, I didn't think about it. Well, eventually we'll do all that. And then I've got root here, 4 times secant squared. Now, I was just saying a minute ago, square roots and exponents distribute across multiplication. That means I can take root 4 times root secant squared. Root 4, that's 2. Root secant squared, secant. Okay, so now we're looking at that. So let's see. If I cancel one pair of 2's, I'm left with that one. So that's going to give me a 1/2, which I would prefer to just remove altogether. I could cancel the secants, and that will leave me a secant on top. So let's say that I'm left with a secant on top, and beneath it I have tangent. So I think that does take care of everything. Okay? And all right, where are we going? Ultimately, what's the goal? To get this in a term that you can work it. To see something there that you recognize that you can work somehow. Okay? All right, so are we there yet? Like, do you know what the antiderivative of secant over tangent is? Maybe you do. I mean, I'm sure there are people that can look at that and just know the answer. Probably you don't, though. So let's see if we can work this out a little bit. Does that reduce to something simpler? Well, I know that when you take pre-calculus or trigonometry, you learn all about identities. You learn more about identities probably than you ever wanted to know. But this is the kind of stuff that you did. You take something that has certain trig functions in it, you, by way of identities, you simplify it into something else. So can we do that with secant and tangent? Secant's 1 over cosine. Tangent is sine over cosine. So that would fairly easily simplify. I'm dividing this fraction by that one. And then we could do that this way. This is 1 over cosine. And this is cosine over sine. Okay? All right. And so, yes, that does reduce to 1 over sine theta. All right. So that's what we're looking at here then. 1 over sine theta. So let's do this. Let's leave the half and write 1 over sine theta. Okay? And now we look at that and decide, well, what can we do with that now that it's reduced a little bit further? Okay, and so for 1 over sine, there's, at least I can't think of any formula for that, the antiderivative of that, but it does strike me that that is cosecant. Okay, and that's one that we've done before. In another video, I think it was the ones on trigonometric integrals. Okay, that lesson. We talked about the integrals of secant and cosecant. All right, so it's something I've showed you before. All right, leading up to this point. All right, so one thing that we learned is the antiderivative of cosecant is natural log cosecant plus cotangent. All right, so okay, so we'll get 1/2 natural log absolute value cosecant theta plus cotangent theta. Okay, and I brought that one up before. All right, so here it is now. So I saw 1 over sine, so I don't know what to do with that. Cosecant, yes, we've done that one before. Here it is. Okay, all right, so we've got our antiderivative. There's the antiderivative. What do we do next? What have we done next for every other problem? We take this antiderivative, we put it back in terms of the original variable. Okay, so can you put this back in terms of x? Like, what's cosecant of theta back in terms of x? Or what's cotangent of theta back in terms of x? And so, oh wait, it was negative, I'm sorry, it was negative natural log cosecant plus cotangent. I forgot a sign. Okay, so we can do that through our original substitution and maybe look at an angle. Maybe see what the angle theta looks like. Okay, so let's take this, explore it a little bit back down here. If x is 2 tangent of theta, then that means tangent of theta is equal to x over 2. Okay, all right. And then the consequence of that is that you could see it like this if you like to see things. Like if you like to see theta as an angle. This side's x, that side's 2 of this triangle. Tangent of that angle is the opposite side over the adjacent side. Okay? All right, so that makes this side over here the hypotenuse 4 plus x squared. Because a squared plus b squared is c squared, Pythagorean theorem. So that gives me a way to get cosecant and cotangent. So you look at this, you say, well, cosecant of that angle, that's hypotenuse root 4 plus x squared over x. And then cotangent, well, cotangent's the reciprocal of tangent, but so that'd be 2 over x. All right, so there's cosecant, cotangent. I go back to my substitution. Solve it for tangent of theta. Well, then you know something about theta. You know something about the angle. You know the tangent. You know 2 sides of the triangle. You could find sine and cosine and all the other trig functions at that point. So, okay. So I get negative 1/2 natural log absolute value. Cosecant is root 4 plus x squared over x. Okay, plus cotangent is 2 over x plus c. All right, and then we get it. All right, but it involves this thing right here, right? We've got to realize that we've done that one before, because otherwise we just get stuck at that point. Okay, so I do this. I use the same kind of substitution, same kinds of identities. This part a little bit different. I show you this one to remind you of that. Okay, all right. So also let's put this as a note, because just so you don't have to look them up all the time. But in another video, I also covered the antiderivative of secant theta. Okay, now that's not involved in this problem. There's no secant, but in case you see that, I'll remind you that what we figured out is that the antiderivative is natural log absolute value of secant theta plus tangent theta. Okay, so also covered elsewhere previously. I've talked about it. I think even in the video that involved that one, I worked it out start to finish. Show you how it was used substitution. But in case you run into it while you're doing this kind of stuff right here, there it is. And also, let's do one more thing. I didn't talk about the fine print, okay? I just put the nature of the starting point and the substitution, and that's all I've talked about. I need to talk about the fine print a little bit. We have the fine print that we restrict the angles between -90 and 90 degrees, just so that the inverse of the trig function works out, okay? Like if you needed to use inverse sine or inverse tangent, we got to think all the way back to pre-calculus for that. But those functions were defined with the angles restricted, so they'd be 1 to 1. So we're just borrowing those restrictions. Okay, so that's some fine print. It doesn't really affect our problems, but I wouldn't be right if I didn't mention it.